Welcome to Theory of Computation. This is lecture number 9. In the last lecture, we actually looked at set theory and a very important technique which is used in set theory called diagonalization. After that, we looked at countable sets and uncountable sets, and we proved that the set of real numbers was not countable. In order to understand this technique of diagonalization, we also proved that the set of all infinite 0-1 sequences is also uncountable. Our goal, of course, is to learn this technique called diagonalization and use it to prove a very important theorem in theoretical computer science, namely the undecidability of halting problem. So, the outline of today's lecture is going to be as follows. We would first look at the halting problem. We will recall the precise definition of it, and after that, we will prove the undecidability of the halting problem. And of course, this is going to be a diagonalization argument, and we would re-examine that proof and identify where we are using this technique called diagonalization. After that, we would discuss something called co-Turing recognizability, and then we will prove another theorem, which is that the halting problem is not co-Turing recognizable. So let us start. What we want to do is study the halting problem. Let's recall what the halting problem is. You're given as input a Turing machine along with a string, and the question is to accept all those pairs of Turing machines and strings where the given Turing machine accepts the string. Formally, ATM is going to be the set of all encodings of M, W, where M is a Turing machine that accepts the input W. This problem, the halting problem, is Turing recognizable. Last time we saw a Turing recognizer for it. Well, let's review this Turing recognizer for the acceptance problem for Turing machines or the halting problem. Suppose this Turing recognizer that we are going to call U, the universal Turing machine, gets an input which is M, W. All it does is simulate M on the string W. And if M accepts, the Turing machine U accepts. Let us ask why U is not a decider. Well, it's very simple. Suppose that M is a Turing machine that loops forever on given input W. Then if I give M, W to the universal Turing machine, the universal Turing machine will also loop forever. Therefore, U is not a decider, but it is a recognizer for this language ATM. And hence, this language is Turing recognizable. Now our goal is to show that this language is not Turing decidable. How does one prove that a language is not Turing decidable? Well, in order to do that, we have to prove that there is no Turing machine which halts on all inputs and solves this problem. The technique that we are going to use in order to prove this theorem is, as I told you, going to be diagonalization. So the theorem that we will prove today is that ATM is not decidable. The proof is going to be by contradiction. A proof by contradiction goes as follows. Suppose you want to prove that ATM is not decidable. So you assume the opposite, that is, you assume that ATM is decidable. And then you follow logical steps from that assumption and show that these, after following certain amount of logical steps, you reach a logical absurdity. Well, since you started with an assumption which led to absurdity, therefore that assumption must be absurd, and hence the negation of the assumption must be true. This method, proof by contradiction, was used by the Greeks early on, and it's sometimes called reductio ad absurdum. We will start by assuming that ATM is decidable and reduce that to an absurdity. So we will use proof by contradiction. We want to prove that ATM is undecidable. So the negation of that statement is that ATM is decidable. What does that mean? That means we will have a Turing machine, let's call this H, for this hypothetical Turing machine, which decides ATM. So if I give H an input m comma w, it will accept m comma w if m accepts the string w. It will reject m comma w if m does not accept the string w. Formally, the behavior of h would be as follows. H of m comma w is going to be accept if m accepts w and reject if m does not accept w. Note that this hypothetical Turing machine halts in all cases. Even when m loops forever on w, somehow h manages to reject that input or reject that pair of input m comma w. If h exists, then we can use it as a subroutine in other Turing machines. Other Turing machines can call this h as a subroutine or can run this Turing machine h on various inputs. So let's make a new Turing machine. Let's call it D. The description of this Turing machine D is as follows. D gets as input only a description of a Turing machine M. It then converts this description M into the pair M comma the description of M. Now it runs this hypothetical Turing machine H on M comma the description of M and outputs the opposite of what H outputs, which means if H rejects its input, then D accepts, and if H accepts its input, then D rejects. Let's think about whether we can make this Turing machine D. What it does is it gets a description of a Turing machine M, and it has to convert the description into M followed by the description of M. That's just a syntactic manipulation. All you have to do is get the description of M and copy it twice and put it as an ordered pair, and that can be done very easily. So this Turing machine D can do the first step that we have described there. Then it runs the Turing machine H on this particular input. Now since H exists, it's a Turing machine, therefore we can have H as a subroutine of D. After that, it just finds out whether H accepts or rejects, and it does the opposite of what H does. Hence, D is a bona fide Turing machine as long as H is a Turing machine. So let's analyze D a little bit. D, what is D doing? It gets a description of a Turing machine and no string, and it converts that description into the description of the Turing machine followed by its own description and then calls H. So D is actually finding out if M accepts its own description or not. Let's see this closely. H will accept the pair M comma the description of M if and only if M accepts its own description. So the Turing machine D is actually finding out whether a given machine M accepts its own description. If the Turing machine M accepts its own description, then D rejects that Turing machine, and it accepts all those Turing machines which do not accept their own descriptions. Can a Turing machine accept or reject its own description? That sounds a bit strange. Let's think about this problem in terms of programs. Can we have a program that we can run on itself? Well, of course. There are some examples that you have already seen. Let's look at a few examples, and this would convince us that this is not an extremely strange idea. Running a Turing machine on its own description is like running a program on itself. One example that comes to our mind is a word count program which is written in C. We can run this word count program on its own code, and it will tell us how many lines of codes did we write in order to accomplish the word count program. Another possibility is you can write a compiler for C which is written in C itself. Now this compiler can compile itself. You can take the compiler, make executable code out of it, and run that code on the compiler itself, and you will get an executable code which is implementation of your compiler. You compiled it using your own compiler. In fact, that's very common. So it's very common to have programs, not extremely common, but reasonably common to have programs that can to which you can give the program as input, so they can take themselves as input. Similarly, we can take a Turing machine and run it on its own description and see what the Turing machine does. Now, this Turing machine D runs or finds out if a machine M accepts its own description or not. If it accepts its own description, then D rejects those Turing machines. So let's look at what D is doing. D on input, which is an encoding of M, will accept if M does not accept its own description, and it will reject if M accepts its own description. Now, there is a very interesting twist in the proof. What we are going to do is simply ask the question, how would D behave if we give it its own description? All right, what would be the behavior of D if D were provided its own description as an input? Let's find out what D is doing. If we give D its own description, it will accept if D does not accept its own description, and D will reject if D accepts its own description. But this is absurd in both cases. What we are saying is D will accept its own description if and only if it does not accept its own description. And that's a logical absurdity. If D accepts its own description, then somehow it should reject its own description. On the other hand, if D rejects its own description, then somehow it should accept its own description, which is a logical absurdity. So let's review what we have done. We hypothesized this Turing machine H, which solves the halting problem. Then from there, we said, if somebody gives us H, we can design this new Turing machine D, which will accept all those Turing machines that do not accept their own description. After that, we said, well, let's see what D would do if we were to give D its own description as an input. And we found out, we reach a logical absurdity that D would accept its own description if and only if it does not accept its own description. Since by following logical steps, we have reached a logical absurdity, the only thing we can conclude is our initial assumption was wrong. And our initial assumption was that this H, a hypothetical Turing machine which solves the halting problem, exists. Therefore, we can conclude that assumption was wrong, which means that there is no Turing machine that can solve the halting problem, and therefore the halting problem is undecidable. Let's review this proof once again, summarize it, and see what we have done. We started by the assumption that H exists. We use H to construct D. This is easy. D simply converts descriptions of Turing machines into pairs. The first component is the machine and the second component is the description of that machine, and calls H. It returns the answer which is opposite of the one given by H. H accepts M, W exactly when M accepts W. D rejects M exactly when M accepts M. Therefore, D rejects itself exactly when D accepts itself. And that is a logical absurdity which has led us to contradiction, and thereby we have proved that the halting problem is undecidable. Once again, we have started with an assumption, followed logical steps, reached an absurdity, and therefore we can conclude that our original assumption was wrong, which was that H exists. Therefore, H does not exist. Therefore, the halting problem is undecidable. The proof that I have described to you that the halting problem is undecidable is only a few lines. If you want, you can write down the proof in 4 or 5 simple steps. However, it's a very, very subtle and complicated proof. If the ideas used in it are extremely subtle, therefore you must carefully go over the proof over and over again in order to really understand what's going on. The most important thing is we started with the assumption that a certain Turing machine exists. You must make sure that all the rest of the steps that we did are logically sound, that we did not create an absurdity within the proof through some false reasoning. Since the end of the proof leads us to an absurdity, therefore, if all the steps are logical, we can conclude that our initial assumption was wrong. Well, I told you that we will be using the technique of diagonalization in order to prove that the halting problem is undecidable. However, this proof, well, it's not very clear that we're using any kind of diagonalization or that it is similar in some sense to the proofs that we did in the earlier lecture. For example, we proved that the set of all real numbers was not uncountable. Remember that diagonalization proofs were characterized as follows. We somehow had an infinite matrix and we looked at the diagonal. Somehow we complemented the diagonal and defined something. Can we understand this proof in terms of diagonalization? It's not very clear, but we can find out that all we are doing in this proof is diagonalization. Where is the diagonalization in this proof? Well, it is hidden, but we can find it. Let's make a matrix as follows. Let's label the rows of an infinite matrix by Turing machines, M1, M2, M3, and so on. Let's label the columns of this matrix by descriptions of these Turing machines. So we put description of the first machine, label the first column with that, and second machine, label the second column with that, and so on. And let's take the ith, jth entry of this matrix to be what the Turing machine mi does on the if you give it the description of the jth Turing machine. So the ith, jth entry is going to be except if mi accepts the description of mj. This matrix would look as follows. The first three entries in the first row tell us that M1 accepts its own description and the description of M3, but not the description of M2, and so on. The second row tells us that M2 accepts descriptions of all possible Turing machines. Similarly, the fourth row tells us that M4 accepts the description of M1 and M2, but not the description of M3. So what we have done is we have created a matrix. We have labeled the columns and the rows. The rows are Turing machines and the columns are labeled by descriptions of the Turing machine. An entry tells us whether this particular Turing machine which labels the row accepts the description of the Turing machine that labels the column. So that's our matrix M. Let's continue now. Now what we can do is we can look at the behavior of this hypothetical Turing machine H that we said exists and make another matrix. Once again, the rows are labeled as before. They are just labeled by different Turing machines, and the columns are labeled as before with the descriptions of various Turing machines. The entry ij is the output of this hypothetical Turing machine on the pair mi, description of mj. Let's look at this matrix and fill these entries and see how it would look like. The first three entries in the first row would be accept, reject, accept. All the entries in the second row would be reject. Similarly, the fourth row, accept. The first entry would be reject, the second entry would be accept, and the third entry would be reject. So what we have done is we have created a matrix which tells us how this Turing machine, this hypothetical Turing machine H behaves. D is going to be obtained by looking at the diagonal of this matrix. Actually, we are going to define D by looking at the diagonal of this matrix. The machine D, when it is given the input, the description of mi, looks at the ith, jth entry and outputs the opposite. Just like in the Cantor's idea, what we did was we are going down the diagonal, and if we look at the diagonal and do exactly opposite of what the diagonal entries are. So D gets an input mi, it goes to the diagonal, finds out what it is, and does exactly the opposite. If H was accepting on the diagonal, then it rejects. If H was rejecting on the diagonal, then it would accept. Now, if D is a Turing machine, if D happens to be a bona fide Turing machine, then D would appear as a label on one of the rows. Let's try to see how does that row look like, and we will reach a contradiction. Here we have filled a row for D. How would the row look like? The columns are labeled by descriptions of Turing machines M1, M2, and so on. The ith entry for the row for D will just be the opposite of the output of H on Mi, Mi. So we'll go to the diagonal and flip it. So we look at the diagonal of the H matrix and flip the diagonal entries in order to get the row for D. Now, if D happens to be a bona fide Turing machine, then it would be labeling one of the rows. Let's look at this row a bit more carefully. The first element of this row is reject because M1 accepts its own description. The second element of this row is going to be reject, whereas the third element is going to be accept. Now, we ask the question, what is going to be, if this D is a bona fide Turing machine, what is going to be the entry in the column which is labeled by D or the description of D? So we're asking, what would D do on its own description? And that's where we get a contradiction. The contradiction comes when we try to find out the entry that corresponds to the column that is labeled by the description of D. If we put an accept there, it should have been a reject. Similarly, if we put a reject there, it should have been an accept. So you can see that the proof we have done is actually nothing but diagonalization. The main idea of the proof is once again coming from Cantor's idea of diagonalization. We can put this proof in the language of diagonalization. This is a spectacular proof. We have shown that the halting problem is undecidable. Let's review this proof once again. Assume that H exists, construct D. We argue that D can be constructed from H. We then check what D will do if it's given its own description. This leads us to an absurdity, therefore H cannot exist. Here, now I can say quad erat demonstratum, which is what we usually do when we end a proof, because we have shown what we were after, that the halting problem is undecidable. Let's recall the definition of what was Turing recognizable. Remember, a language is decidable if we can find a decider for it. A decider is supposed to classify the strings, whether they are in the language or not, and halt on all inputs. What does it mean for a language to be Turing recognizable? All we want it to do is design a Turing machine that would accept all the strings that are in the language, and it will not accept all the strings that are not in the language. What I have written down on the slide is a very simple theorem which says that a language is decidable if and only if its complement is decidable. The proof is actually one line. If we have a decider M that accepts A, then we can switch the accept and reject states of this decider M to obtain another decider. Now this other decider M prime will accept the complement of A. So if you have a decidable language, you can take a decider for that language, and we can switch the accept and reject states of this decider, and what we obtain is a decider for the complement of that language. So if a language is decidable, its complement is also decidable. We can say this fact in another way. We can say that decidable languages are closed under complementation. So if you take the complement of a decidable language, you get another decidable language. Well, how about Turing recognizable languages? Let's first recall the definition of a Turing recognizable language. I call a language Turing recognizable if I can find a Turing machine which accepts all the strings that are in the language and which does not accept all the strings that are not in the language. So let's recall that a language A is Turing recognizable if there is a Turing machine M such that L of M equals A. the TMM does not have to halt on all inputs. All we want is that M, when given the input X, will accept if X is in A and will not accept if X is not in A. So, note that the same trick of the previous theorem will not work here. Suppose you have a language which is Turing recognizable and you have a recognizer, a Turing machine M, whose language is the given language. If you switch the accept and reject states, the new Turing machine is not going to accept the complement of the original language. Why is that? Well, let's look at this behavior of this Turing machine M prime on a given input X. M prime on X will reject if X is not an element of A complement, which means X has to be an element of A. And it will either accept or loop if X is an element of A complement. But this is not the same as having the language of M prime equal to A complement. In fact, what happens is the language of M prime, we're sure that it's a subset of A complement. But that's all we can say about it. It may be a proper subset, and typically it would be a proper subset. It would not be all of A prime. M prime will not accept all the strings that are not in A. Therefore, this trick does not show that Turing recognizable languages are closed under complementation. In fact, we will see later that Turing recognizable languages are not closed under complementation. Since Turing recognizable languages are not closed under complementation, so it is sensible to talk about a language whose complement is Turing recognizable. Therefore, we make the following definition. A language B is called co-Turing recognizable if B complement is Turing recognizable. So we call a language B co-Turing recognizable if its complement is Turing recognizable. Now what we are going to do is we will relate Turing recognizable, co-Turing recognizable with our previous concept of decidability. We want to prove the following theorem. If a language is Turing recognizable and co-Turing recognizable, then it is decidable. So a language, if you can establish that it's Turing recognizable, you can also establish that its complement is Turing recognizable, then from there you can conclude that the language is actually Turing decidable. How will we prove this theorem? Well, we'll use the technique called that we have used before in this course called dovetailing. The idea is as follows. If a language is Turing recognizable and its complement is Turing recognizable, then we can find two Turing machines, one which accepts the language and the other which accepts the complement of this language. We can take these Turing machines and run them in parallel and find out if a given string is accepted by one or the other. And that will tell us whether that string is in the language or not, and we can answer accordingly. Let's look at this proof in more detail. Suppose A is Turing recognizable and co-Turing recognizable. Then since A is Turing recognizable, there is a Turing machine M1 such that the language of M1 is exactly equal to A. Since A complement is also Turing recognizable, there is another Turing machine M2 such that the language of M2 is A complement. Well, this means that if X is in A, then M1 accepts X. If X is in A complement, then M2 accepts X. Now let's construct a new Turing machine. This new Turing machine is going to be made out of M1 and M2. The description of this Turing machine is as follows. When it gets an input X, it runs M1 and M2 on X in parallel. If M1 accepts X, it accepts. If M2 accepts X, it rejects. So how can we run two Turing machines in parallel? The idea is once again to use dovetailing. So a more detailed description of this Turing machine is given as follows. On input X, place the starting configuration of the first Turing machine M1 on X on one of the tapes. Place the starting configuration of M2 on X on your second tape. Now, for I going from 1, 2, and so on, what we will do is simulate one step of M1. If M1 accepts, we'll accept. And then simulate one step of M2. And if M2 accepts, we will reject. So, what we're doing is running both simulation of M1 and M2 simultaneously. What would be the language accepted by this new Turing machine N? Let's have a look at it. If X is in A, then N accepts X. And if X is not in A, then N will reject X. Therefore, the language of N is going to be A. Furthermore, N is going to halt on all inputs. This is because the union of A and A complement is all of sigma star. If you give X as an input to this Turing machine, then either X is in A or X is not in A. If X is in A, eventually M1 will accept, and therefore N will accept and halt. On the other hand, if X is not in A, then M2 will accept, and therefore eventually N will reject the input. So all inputs will be either accepted or rejected, and this Turing machine halts on all inputs. Furthermore, the language of this Turing machine is A. Therefore, N is a decider for A, and hence A is decidable. So we have shown that if a language is Turing recognizable and it's also co-Turing recognizable, then that language must be decidable. A language that is Turing recognizable and co-Turing recognizable simultaneously is decidable. This is theorem 4.16 given in the book. The theorem precisely says if a language is Turing recognizable and co-Turing recognizable, then it is decidable. What we want to do is to apply this theorem to the halting problem. However, we will not be able to apply this theorem directly. What we have to do is gather all the information that we know about the halting problem. What do we know about the halting problem? One is that it is Turing recognizable. Two is that the halting problem is not decidable. We can take all this information and apply this theorem to conclude more about the halting problem. Let's go back to the halting problem and look at it from the point of view of this theorem. We know that ATM is Turing recognizable. The second thing we know about ATM is that it's not decidable. So what can we conclude using this theorem? We conclude that the complement of ATM is not Turing recognizable. Why is that so? How can we conclude that the complement of ATM is not Turing recognizable? Well, we can argue as follows. We can argue by contradiction again. We know that ATM is Turing recognizable. Suppose the complement of ATM was also Turing recognizable, then ATM would have two properties. One is that it would be Turing recognizable. Two, it would be co-Turing recognizable. And therefore, by theorem 4.16, we can conclude that ATM is decidable. However, we've already proved that ATM is not decidable. So, theorem 4.16 will lead us to a contradiction. Therefore, our assumption that the complement of ATM was Turing recognizable must be wrong. This is another theorem that we will prove right now. It says that if A is a language and if A is not decidable, then either A or its complement is not Turing recognizable. We will see that this theorem is just the contrapositive of theorem 4.16. Let's suppose that A is not decidable. Also, let's suppose that the complement of A is Turing recognizable and A itself is Turing recognizable. Then what would theorem 4.16 give us? Well, it will tell us that A is decidable. However, we've already said that A is not decidable. This leads to a contradiction. Therefore, we can conclude that if A is not decidable, then either it or its complement must not be Turing recognizable. This theorem is just the contrapositive of theorem 4.16. In order for us to understand it that way, what we have to do is to recall what a contrapositive is. Let's recall a few basic definitions that you've learned in your discrete math classes and actually see that this theorem is nothing but the contrapositive of theorem 4.16. Let's recall that if we have a statement S which is of the form P implies Q, then the contrapositive of S is not Q implies not P. So suppose you have a statement S which is of the form P implies Q, then its contrapositive is the statement not Q implies not P. Suppose you have established a theorem which is of the form P implies Q, then you have also established the theorem of the form not Q implies not P. In a statement of the form P implies Q, P is called the premise and Q is the conclusion. So you have some premise which allows you to conclude something else. So you have a premise P which allows you to conclude a conclusion Q. Now suppose somebody tells you that the conclusion is false. Then what can you conclude from that information? Well, from this information you can conclude that the premise must have been violated. Suppose that if someone walks in the rain, then they get wet. So you have the premise that someone walking in the rain, someone has been walking in the rain. From that you can conclude that their clothes get wet. Now if somebody comes from outside into your room and they tell you that they've been walking outside and you realize that their clothes are not wet, then from that you can conclude that it must not be raining outside. So that is the way we use contrapositive. If we know that some premise implies a conclusion and somehow we find out that the conclusion is not true, then we say that the premise must have been violated. So let's take the contrapositive of theorem 4.16 and see that we get our new theorem. Now suppose we have a statement of the form P1 and P2 implies a given conclusion Q. Then what would be its contrapositive? Its contrapositive would be not of Q implies not of P1 and P2. However, we can apply De Morgan's laws to the right-hand side of this, which tell us that not of P1 and not of P2 is the same as not of P1 or not of P2. That when you simultaneously negate an and of two things, then that's the same as negating each thing and oring them. Hence, the contrapositive of the statement P1 and P2 implies Q becomes not Q implies not of P1 or not of P2. So P1 and P2 implies Q, then not of Q implies not of P1 or not of P2. We can simply think about it this way. If two things together allow us to conclude something and we realize that the conclusion is not being satisfied, then we can from there argue that one of those two things must not be satisfied. So if P1 was true and P2 was true, and that allowed us to conclude Q, and someone told us that Q is not true, then either P1 would have been violated or P2 would have been violated. In theorem 4.16, we take P1 to be the statement that A is Turing recognizable. We take P2 to be the statement that the complement of A is Turing recognizable. Then theorem 4.16 says that from here we can conclude that A is Turing decidable. A is Turing recognizable and a complement is Turing recognizable implies that A is Turing decidable. So the contrapositive of this would be that if A is not decidable, then either A is not Turing recognizable or its complement is not Turing recognizable. So our new theorem is nothing but the contrapositive of theorem 4.16. Now, this new theorem is easier to apply if we think about the halting problem. What do we know about the halting problem? Well, one, we have proved today that the halting problem is not decidable. We also know that the halting problem is Turing recognizable. So when we put all that information into this theorem, we put the premise that the halting problem is not decidable. We can conclude that either it is not Turing recognizable or its complement is not Turing recognizable. However, we already know that the halting problem itself is Turing recognizable. This means that the only possibility is that its complement is not Turing recognizable. So, from this theorem, we can conclude that the complement of the halting problem is not Turing recognizable. So today what we have done is we have been able to show that there are problems, and in fact we have identified a problem, the halting problem, and shown that it is not decidable. Then we also saw that the halting problem is Turing recognizable. It is very easy to make a Turing machine that recognizes ATM. All it does is simulates M on W, and if M accepts W, then it accepts. Then we looked at the concept of co-Turing recognizability. We made the following definition that a language is if it's called co-Turing recognizable if its complement is Turing recognizable. After that, we proved a very nice theorem which said that if a language is Turing recognizable and also co-Turing recognizable, then it must be decidable. We then looked at our knowledge about the halting problem. The halting problem is not decidable and the halting problem is Turing recognizable. From there, we concluded that the complement of the halting problem cannot be Turing recognizable. So, the complement of halting problem is an extremely difficult problem. Not only it's not decidable, but it's not even Turing recognizable. That's extremely difficult. So, no one can ever make a Turing machine which will accept exactly the complement of the halting problem. Even if such a Turing machine were allowed to not halt on many of the inputs, it's not possible to make a Turing machine whose language is exactly the complement of the halting problem. The main ingredient of all that we did hinged upon this one idea that we call diagonalization. In the last lecture, we looked at how diagonalization was used in set theory to prove the existence of uncountable sets. Today, we use the same idea of diagonalization to show that the halting problem is undecidable. I would like to discuss how important it is for us to show that the halting problem is undecidable. Firstly, note that we have not just said that there are undecidable problems. We have actually identified one. This halting problem is going to help us in proving many other things. We will be able to show that many other problems are not decidable. How are we going to do that? Well, we will show that if we were able to solve these other problems, that would allow us to solve the halting problems. So, another problem which can help us solve the halting problem must be undecidable. Let's look at another problem on which we can apply these ideas. Let's consider the following question shown to you on the slide. Can we have an enumerator which enumerates the descriptions of all those enumerators that do not enumerate themselves? This is a very concrete problem. So I'm asking, can you ever build an enumerator? Remember the model of enumerators that we have discussed before. Enumerators are machines which do not take any input, but when you turn them on, they start writing outputs. Okay? and the set of all things that they write on their output tape is called the language of that enumerator. So now I want to ask if it's possible to design an enumerator which will enumerate exactly and only those enumerators that do not enumerate the description of themselves. Let's think about this for a moment. Would it be possible for us to design an enumerator which will enumerate exactly those enumerators that do not enumerate themselves? In order to see that such an enumerator doesn't exist, all we have to do is ask the following question. Will this enumerator enumerate its own description? Well, let's think about it. Suppose this enumerator enumerates its own description. Then, since it was required to only enumerate those enumerators that do not enumerate their own descriptions, therefore, it should not have enumerated its own description. Now, if this enumerator does not enumerate its own description, then by its very definition, it should enumerate its own description. So we run into a contradiction either way. Hence, such an enumerator cannot exist. Actually, this problem is motivated by one idea of the great philosopher Bertrand Russell. He used this idea to show that there are paradoxes in set theory, and we would not actually look at Russell's paradox in that setting, but we would look at it informally. Russell asked the question, can there be a barber which shaves exactly those people who do not shave themselves? The way he explained that such a barber cannot exist by the very definition of it is because would the barber shave himself or not? If he is expected to only shave those people who do not shave themselves, then if he shaves himself, then he should not be shaving himself. And if he does not shave himself, then he should be shaving himself. And so either way, whether he shaves himself or not, we reach a contradiction, and therefore we can conclude that such a barber does not exist. So diagonalization is an extremely important, beautiful idea in computer science and mathematics. It's used in many places such as set theory and studying cardinal numbers. In computer science, it's used in computability theory to prove that problems are undecidable. Later on, we will use diagonalization in complexity theory to obtain very interesting results. Therefore, I hope that you would try to spend time on this very idea of diagonalization. It is an extremely central theme in this course. The proof of undecidability of the halting problem uses diagonalization. It's a very short proof. It's very easy to understand. However, it's also very easy to forget, and it's also very easy to make mistakes. It's a very subtle idea. Therefore, I hope you will spend a lot of time on the proof of undecidability of the halting problem. I hope to see you next time. Thank you and goodbye.